Can you hear me, folks?
Yes.
Yes.
All right. So let's wait another minute and then again, this was a mandatory class because this is a recitation slot. It is mandatory, so I expect everybody to be here. Give me a second. All right, folks, let's begin. So in the last class, we sort of introduced neural networks and showed how they were capable of computing pretty much any function, right? So in this class, we will try to get a better idea of what a neural network can represent. Now, the key word here is can. What this means is that we are going to be talking about, about whether it's possible in theory to construct a network to represent any given function if we are not telling you how to construct the function. So the topics for the day are what can neural networks represent? And what are the restrictions in terms of depth, width, and activations? So overall, here's what we've learned so far. Neural networks have taken over pretty much most of AI. And here are a bunch of different tasks that were made possible by neural networks, also known as deep learning these days. These tasks were once assumed to be purely in the domain of human expertise, but now machines can routinely recognize speech, perform translation, and even even create. So neural networks have achieved what seemed to have been impossible just a few years ago. Why so? So what are these neural networks? These are these boxes that take in some input and generate an output. So they could take in a voice signal and generate a transcription, take in an image and generate a caption, and so on. But what's inside these boxes? And we found that the way to think about these boxes is to think about it in terms of the capacity of the human brain, because these functions here in humans are computed by the human brain. And so in their basic form, neural networks mimic the network structure of the brain. So we saw that the brain is composed of a network of neurons, where each neuron in turn has the structure where it gets inputs from many neurons. And if the cumulative input exceeds some threshold, the neuron fires. That signal goes out to other neurons. These individual neurons can be mathematically modeled roughly in this manner. Each neuron has several inputs. Corresponding to each input is a weight. So the neuron receives a weighted sum of all of these inputs. And this weighted sum is then compared to a threshold in the most basic form of the neuron. If the weighted sum exceeds the threshold, the neuron fires. Otherwise, it does not. Now, these perceptrons we saw are capable of these units. We call them perceptrons. They are capable of computing certain classes of Boolean operations. But to make them generic, we needed to be able to network them. And so to emulate the human brain, we actually composed networks of these basic units. So once again, the basic unit is looks like this. It computes a weighted sum of inputs and compares it to a threshold. The output is 1 if the weighted sum exceeds a threshold, and 0 otherwise. Electrical engineers will recognize this as a threshold gate. It's a basic unit of Boolean circuits. Now, instead of comparing a weighted sum to a threshold, I can also do it somewhat differently. I can say I'm comparing summation wi xi minus t to 0. And so these two are exactly the same operations, right? Both of these are the same operations. Now, where will this term over here, where is the boundary between where the function, the perceptron outputs a 0 and where the perceptron outputs a 1? Where's the boundary? Anybody? Where would this boundary be? Anyone? The boundary is going to be in the input space. The boundary is going to be where summation wi xi is exactly equal to t, correct? What is this an equation for? What is this an equation for? Anyone? This is a hyperplane, right? And where does the, so it's going to be, in general, it's going to be, if you think of an input space of this kind, in two-dimensional input space, this is going to be a plane of this kind. So a plane of this kind that doesn't go through origin has this format, which is summation wi xi minus t, or more generally, I can write this as summation wi xi plus b, right? This plus b, the b is the same as your minus t. So this function, when you equate it to 0, it's going to give you, it's the equation for a hyperplane that does not go through origin. So what do we call such functions? Functions which, when equated to 0, give you the equation of a hyperplane that does not go through origin. What do we call them?
Affine.
Affine functions, correct? And if they actually, where is my, well, I cannot see my mouse. Okay, and if it actually went through the origin, what would you call it? Linear. In that case, it's going to have the form summation wi xi equals 0. There's no b, right? So this perceptron can be rewritten in this manner. The perceptron can be rewritten as a first computing, just as we said, you're computing a weighted sum of the inputs plus a bias, and you're comparing it to 0, right? So you can rewrite the perceptron as first computing an affine function of the inputs, some affine function z, which I'll call an affine value, which is summation wi xi plus b, and then putting this value z to a second function, a threshold function, which outputs a 1 when the input is positive and 0 otherwise. So these two are exactly the same unit, right? And so once I redraw things in this manner, I can actually change this threshold activation to something different, like a soft thresholding function, what we call a sigmoid, where the output goes rather smoothly from 0 to 1, rather instead of going from 0 to 1 in this sharp manner. And here's an equation for the sigmoid. We will see this again. And we can also replace this activation with other kinds of functions like tan h's, or these functions we see to the right, which we will also encounter later in today's lecture. Anyway, for now, I'm going to continue assuming that we have a threshold function. This is what we will call an activation function. And so I'm going to continue assuming a threshold activation because it makes the presentation of some of the intuition very clear. Now, before we continue, here's a poll. It is Okay, 10 seconds, guys. All right, I'm ending the poll because. All right, so can you answer me? Is this first one, is it linear or affine? Is this first one linear or affine?
Linear.
Linear.
Linear? Okay, what about the second one?
Affine.
Is it linear? It's okay. What about the third statement? Is this true? 3x plus 7y is affine.
Yes.
Because linear functions are also affine functions, but not affine functions are not linear functions. Is this fourth statement true?
Yes.
True.
Right? So 3x plus 7y plus 4, it has a bias, it's affine. This doesn't have a bias, but still it's affine. It's with a bias of 0. This has a bias, so it's a linear combination. This has no bias, so this has a bias, so it's not a linear combination, it's affine. And this has no bias, so it's a linear combination. Anyway, moving on. So a multi-layer perceptron is going to be a network of such units. You have many network neurons, and the individual perceptrons feed other perceptrons. Now, our definition of the term we use is a multi-layer perceptron. So we need to know what we mean by a layer. But first, we are talking about deep neural networks. What does it mean for a network to be deep? Does anybody know?
2 or greater than.
2 or great what?
Hidden layers.
2 or greater.
Hidden
When
layers.
it has more than one internal hidden layers.
Do they have to be
Multiple
hidden layers?
layers, and in between layers there are activation functions.
Okay, so here's how we define deep structures. In any directed, when I'm speaking of a perceptron, it's a weighted sum of, a perceptron is really this entire operation, which is computing an affine term and putting it through an activation first. Second, in any directed graph with an input source and an output sink, the depth of the graph is the length of the longest path from source to sink. So in this graph, I've got a path of length 1. I also have a path of length 2. So the depth of this graph is 2. This graph, it's got a source, it's got a sink, all the edges are directed. You have a path of length 1 from source to sink. You also have a path of length 2. But the depth of the graph is 3 because the longest path is 3 in length. That clear? What we mean by the depth of a graph? Yes or no? I'd like to see a few more yeses. Yes. So please give me a thumbs up or give me a yes so I can continue, right? Okay. So in a multi-layer perceptron, the output occurs at a certain depth from the input. A multi-layer perceptron is actually a directed graph. And so if the depth of the output layer is greater than 2, it's called a deep neural network. So this guy over here, if each box represents a layer, and this is the input, is this one on top a deep neural network? The one on top? Yes or no? What's the depth of this network? Anybody? 2, right? So it's not deep. This one over here, would this be deep or not? And what's the depth of this network?
4.
4, right? Yes. Okay. But we're speaking all along of layers. What do you understand by layer? Anybody want to take a guess? What is a layer?
the group of
Anyone?
neurons in the same depth.
Nodes at the same depth with respect to the input. So a layer is the set of neurons that are all the same depth with respect to the input, not the source, not the sink, I'm sorry, right? So if I see a network of this kind, these guys, all the red neurons are the first layer. Although visually, these appear to be the second layer and this is the first layer, all of the red neurons are at depth 1 with respect to the input, so they form the first layer. The green neurons are all at depth 2 with respect to the input, meaning the longest path to the green neurons is 2. Now observe that this green neuron also has a path of length 1, but its depth is 2. So these green neurons form the second layer. These two yellow neurons form the third layer, and the blue neurons form the fourth layer. So a deep network that has at least 3 layers. Now, in a multi-layer perceptron, so this clear? Yes or no, guys? It's okay.
Master, can you see the comments in the chat?
Pardon me?
Can you see the comments in the chat?
Yeah, I'm seeing the chat, I'm watching the chat on the side.
Okay,
Because
I'm
they're
just making
flying
sure.
by, right?
Yeah.
Yes. So now we also saw in a multi-layer perceptron that the inputs could be real or Boolean. The outputs could be real or Boolean. Now, in this kind of network, what can the network compute? What kinds of input-output relationships can a network model? We saw this in the last class already. We saw that MLPs can compose Boolean functions. And specifically, if you give me any odd Boolean function, I can compose a network. I can create a network that computes that Boolean function. Similarly, you give me any odd real valued function, and I can compose an MLP that approximates the real function to arbitrary precision. So what are the limitations? That's what we're going to be covering in the rest of the lecture. We're going to be talking of multi-layer perceptrons as universal Boolean functions and the need for depth, as universal classifiers and the need for depth, and as universal approximators, and once again, the need for depth. So let's look at this first topic. How well do MLPs model Boolean functions? Now, we've already seen that a perceptron can model, a single perceptron can model any simple binary Boolean gate. So using the notation from the last class, this perceptron to the left, what was it? What gate was it?
And
And, right? And this guy here,
or
and this was a NOT, right? But then it can do something far more complex than this. So here is what I call a universal AND gate. This perceptron has n inputs, but it will only fire if all of the first L inputs are 1 and the remaining inputs are all 0, right? So can you see why this is the case? Anybody? Can somebody take a shot at explaining why this is so? Okay, if nobody wants to. Okay, let's see this. If the first L inputs are 1 and the remaining inputs are 0, then what is the total input coming into this over here? What is the total input?
1.
Right? Because you have L ones and the rest are zeros. Now, if any of these becomes a 1, what happens to the total coming here? Does it increase or decrease?
Decreases.
Decrease.
Becomes L minus 1.
If any of these becomes a 0,
It's also less than.
then also a decrease. Correct? So the only condition under which the total input matches L is if the first L are all 1 and the remaining are all 0. So here's a perceptron. This is a universal AND gate. You give me an AND clause with a certain number of, or acceptances and negations, and I can build a perceptron for it. Now, here's a universal OR gate. This one will fire if any of the first L are 1, and if any of the remaining L, or if any of the remaining L are 0. So if any of the red ones are 1, or if any of the green ones are 0, this is going to. Can somebody try to tell me why why that would be the case? Okay, let me explain. What is the only condition under which it will not fire?
That's when all of the x1 through xl are 0, and all of the xl plus 1 through xn are not 0.
Right?
Yeah.
Yeah, are they when they're 1? At that point, the total input is going to be L plus n, right? Because that's how many L minus n, because that's how many green units you have. If any one of the rest flips, then the total is going to exceed L minus n. So using a threshold of L minus n plus 1, this gives me a perceptron that's going to fire if any of the red inputs are 1, or if any of the green inputs are 0. So it's a pretty powerful thing, right? But here's something even more impressive. This is a majority gate. It has n inputs, and it will fire if at least k of the inputs are 1. Can you see why? Anybody?
K is greater than n by 2.
It doesn't matter. If any k of the inputs are 1, right? At least if at least k of the inputs are 1, it's going to fire. Can you see why that's the case?
That's all good.
The threshold is
What happens? Yeah. What happens if fewer than k inputs are 1? What is the total that comes in?
If fewer than k
Less than k,
are
right?
1, then yeah, it's less than k, so it doesn't matter. It's not going to fire. The threshold is
Yeah.
if
So,
it's
but
k
if
or
k are
greater.
1, it's going to, if k or greater than 1, it's going to fire. So this is a generalized majority gate. If k is n over 2, then it becomes a majority gate, right? So to build this simple operation using simple regular Boolean gates, if you want to build a majority network, it's going to be exponentially sized in the input. But that can be done using a single perceptron. So which is why way back when people thought that a single perceptron could be a universal Boolean function, that it could compute any Boolean function, because it could compute some classes of functions that using regular Boolean gates would need exponentially sized circuits. But then we find that a simple perceptron cannot compute an XOR. We already saw that. To compute an XOR, we actually need a network of at least 3 perceptrons. Or we can actually get away with 2, but a naive implementation would require 3 perceptrons. This one computes X or Y. This one computes not X or not Y. And then you add the 2, and this is going to be an XOR. And in fact, it turns out you can do it with only 2 perceptrons using this circuit. I actually got this from my friend Gerald Friedland in Berkeley. I won't actually explain this. Let's stay with this little circuit for now. So if I had 3 perceptrons, I can compute an XOR. And so we see that because perceptrons can model Boolean functions, but they can also model things that are more complex than Boolean functions. It means that for any odd Boolean function, I can construct a multi-layer perceptron that can compute this Boolean function. And so MLPs are what are called universal Boolean functions. What this means is that you give me a Boolean function, and regardless of the complexity of the function, I can compose an MLP that will compute it. So MLPs are universal Boolean functions. They can compute any function over any number of inputs and any number of outputs. They can be designed to compute any function over any number of inputs, any number of outputs. But then, how many layers will the MLP need? So for example, for this ugly function, I have 2 hidden layers. This MLP has 3 layers. what is the smallest number of layers that an MLP will require to compute a Boolean function in the worst case? Anybody? Can 2? 1 hidden layer. That's correct, right? And why is that? Can someone tell me? Let me explain. Any Boolean function can be written as a truth table, correct? Yes or no? Basically, I'm listing all of the input variables and the output variable. This is the set of all, so these are all the combinations of inputs and the corresponding outputs. I only need to list the portion of the table that corresponds to the output 1, because for the rest of the inputs, the output is 0. Now, anytime you give me a truth table of this kind, I can write this as a disjunctive normal form formula, a DNF formula. Now, a DNF formula has several clauses. The pluses represent OR, the concatenations represent AND. So this first clause over here, not x1, not x2, x3, x4, not x5, means that x1 takes the value 0, x2 takes the value 0, that's not x2, x3 takes the value 1, x4 takes the value 1, x5 takes the value 0. And so this first clause becomes 1 anytime the inputs follow the pattern 0, 0, 1, 1, 0. The second clause similarly is going to take the value 1 anytime the input takes the pattern 0, 1, 0, 1, 1. This takes the value 1 when the input becomes 0 because it's x1, not x1, x2, x3, not x4, not x5. So it's 0, 1, 1, 0, 0. Similarly, this one is going to be x1, not x2, not x3, not x4, x5. So I get one of these clauses for each one of the input patterns for which the output becomes 1. And if the input falls into any one of these clauses, then that corresponding clause is going to take the value 1, and the overall function takes a value 1 as a consequence. For other input patterns, none of these clauses will trigger, and the output remains 0. So is this making sense to you guys? Give me a yes or no. Give me a thumbs up. I see only one thumbs up. Please respond, folks, because I do tend to wait to see your responses. Now, once I can write it in this manner, here's what I can do. Because the perceptron is a universal AND gate, I can have one perceptron for the first clause, one for the second, one for the third, one for the fourth, one for the fifth, one for the sixth, or them all, and I get an MLP that computes this function. And because any truth table, any function can be represented as a truth table, and because any truth table can be expressed as a DNF formula, I can compose a one hidden layer MLP to compute the function. So a one hidden layer MLP is a universal Boolean function, right? So, but then if I do things in this manner, what is the largest number of perceptrons required in the single hidden layer for an n input variable function? Anyone? So Athena, the answer is, yeah, I'm just using the network and MLP interchangeably. So Siddharth, why is it 2 raised to n?
Each of the variables can be either 0 or 1. So all the combinations would be 2 power n probably.
But is that, but would you really construct that? Would you try to compress it? So let me show you how. How many of you have heard of Carnot maps? Have you heard of Carnot maps? Okay, so what is a Carnot map? For those of you who don't know, Carnot maps are a topological way of representing Samahati, a hidden layer is because the hidden layer, the neurons from the hidden layer are not part of the output that you read. That's why we call it hidden. So a Karnaugh map is a topological way of representing inputs. Here, for example, I have an input of 4 bits. I'm grouping them into 2 sets of 2. So I have W, X, Y, and Z as my 4 inputs. These represent all combinations of W and X. These represent all combinations of Y and Z. So any given cell over here is going to represent a specific combination of all 4 bits. But then there's something very specific about this organization. If you look at 2 adjacent rows, they always differ in only 1 bit. In fact, the top row and the bottom row also differ in only 1 bit. So the top row is a neighbor of this bottom row. So also if you look at any 2 columns, they always only differ in 1 bit. And the leftmost column also is a neighbor of the rightmost column. So this map is actually a torus, where these 2 edges meet and these 2 edges meet. And the cells on this map represent all 16 combinations of the input bits. And now I can represent my truth table by simply highlighting the combinations where the output is 1. This making sense to everybody? Those of you who didn't know about Karnaugh maps, is this making sense? Right, okay. And so because there are 7 clauses over here, I can build a simple DNF formula with 7 terms. But then this topological structure simplifies things. I can group these 4 together. They're all neighbors. When I group these 4 together, what I'm finding is that regardless of the value of W and X, so long as Y and Z are both 0, the functions are going to output 1. So these 4 together simply become a single clause representing YZ equals 0, 0, which is not Y, not Z. Similarly, I can group these 2 together. And when I group these 2 together, this is basically saying that the network is going to fire, the function is going to fire when W and X are 0 and 1, and Y is 0. The value of Z does not matter, right? So this group gives me not W, Y, not W, X, and not Y. Similarly, I can group these 2 guys together, which are also neighbors, and it's going to give me not X, Y, not Z. In fact, I could group all 4 commas together. And so now, although there are 7 clauses, my reduced DNF formula only has 7 combinations for which the output is 1. My reduced DNF formula has only 3 clauses. And now, so when you want to compute a Boolean, construct a Boolean function, you want to construct the DNF formula with the smallest number of clauses. That way, the function is going to be small. And if you build a 1 hidden layer MLP, that too is going to be small. So if I want to construct the most compact MLP, 1 hidden layer MLP for any given function, I'm going to try to reduce the number of clauses in the DNF formula. Is that making sense to you guys? Yes, no? Okay. And you can only combine, there was a question. The four corners are also a group, right? Now, what kind of truth table can never be compressed by grouping? Anybody? Which truth table can never be compressed by grouping?
Alternating.
A checkerboard, right? So this guy can never be grouped. And if this is not groupable, then how many clauses will my DNF formula have in this case? Basically, how many neurons will I have in the hidden layer if I construct a 1 hidden layer MLP? In this case, it's going to be 16. In the more generic case, it's going to be 2 raised to n minus 1. Here's a Karnaugh map with 6 variables, right? And in this 6, again, every alternate box is highlighted. And so, there's no grouping possible. In general, you're going to require 2 raised to n minus 1 perceptrons in the hidden layer, which is exponential in n. And so Here is my second pole, which is can you guys see the pole?
Not yet, no.
Now,
Yes.
okay, 10 seconds, guys. All right. So what is the answer? Anyone? 2 raised to 10 minus 1, 512, right?
Yeah.
So it's very large. But then, so this is going to require, in the worst case, a function over n variables is going to require 2 raised to n minus 1 perceptrons in the hidden layer. It's exponential in n. How many units if we use multiple hidden layers? Can anyone guess? Let me give you an answer. This is an XOR, right? It's an XOR of, basically an XOR is a function which flips if one bit flips. So in a checkerboard, anytime you move sideways by one box, the output flips. So this is an XOR. It's W XOR X XOR Y XOR Z. Similarly, this is U XOR V XOR W XOR Y XOR W XOR X XOR Y XOR Z, right? And an XOR, how many neurons do we need to construct an XOR? Anybody? How many neurons do we need to perceptrons do we need to construct an XOR? 3. An XOR takes 3 perceptrons, or even 2, right? 3 or 2, right? So here's what I can do. This guy, I can use these 3 perceptrons to compute W XOR X, then these 3 to XOR that output with Y, and these 3 to XOR that output with Z. And so instead of here, I can compose this function using 9 perceptrons, or if I use 2 neurons, 2 perceptrons per XOR, I can do this with 6. Now here, maybe this, in both cases, you need the same number of perceptrons, but if I go up to the 6 variable XOR, I have 5 XORs. Each of the XORs is going to require 3 perceptrons. So this one, in the naive case, I needed 33 perceptrons in all. But if I realize that it's just a sequence of XORs, and if I let the network be deep instead of just having one hidden layer, then this network is only going to require 15 perceptrons. More generally, if I have an XOR of n variables, I'm only going to require 3 times n minus 1 perceptrons if I let the network be deep. Whereas, so here's the situation you have. If you have a single hidden layer, you're going to require 2 raised to n minus 1 plus 1 perceptrons in all. This plus 1 is for the final OR. So this is exponential in n. Whereas if you let the network be deep and have multiple layers, then you can do this with just 3 times n minus 1 perceptrons, which is linear in n. So going from one hidden layer to a deep network reduces the number of neurons you require from being exponential in n to just being linear in n. That makes sense? Yes or no? Okay. But then it gets better, right? Here's what. Here's something about XORs. XORs can be, XORs are associative. So I can group them in any manner. So if I have n variables, I can XOR the first 2, then I can XOR the next 2, and then I can XOR their outputs. And I can keep grouping things in this manner. So I can lay the n variables out side by side. I first compute the XOR of XORs of variables pairwise. Then I compute the XORs of their results pairwise and keep doing this, and this output is going to be the XOR of all of these variables. If I redraw the network in this manner, how many layers will I require? Anyone? How many layers will I require? For n inputs. It should require the number of blocks. You're going to need log n blocks. Each block has 2 layers. It's going to require 2 log n layers, right? This making sense? It requires 2 log n layers. Yes or no? Okay. And so now, suppose I just said you're only allowed to use. So this is the least deep network you can compose for this problem, and it's going to require 2 log n layers. But suppose I said you're only allowed to use 5 layers, then what happens? If I put a cap on the number of layers, basically in the best case, it means that you're going to keep grouping up things in this manner till you have only 1 more layer left. And then that final layer is going to be exponential. This final layer is going to be exponential. Final hidden layer is going to be exponential in size in the number of variables that you have at this point. So if I give you a fixed number of hidden layers, only k hidden layers, the circuit is still going, the network is still going to be exponential in size, because the first few layers will keep reducing the number of variables by factors of 2. But then whatever is left, you still have an XOR. And so this hidden layer must compute an XOR over all of these variables, and it will be exponentially wide. So you need at least 2 log 2 n layers. But if you have if the network is required to have fewer than those number of layers, then the network can become exponential in size. That makes sense? Yes or no? Okay. So, questions, anybody? And if you don't give it an exponential number of neurons, the network cannot model the function. And so the actual number of parameters in a network is the number of connections. So here there are 30 connections, because this is the number that really matters in software or hardware implementations. But networks that require an exponential number of neurons would require an exponential number of weights. So the logic is not changed. So Julio, do you understand why you have log n blocks here?
Yeah, I don't get why.
So if I keep grouping n variables pairwise, how many times can I group them?
Sorry, if you group variables,
If I group variables, n variables pairwise, how many times can I group them? If I start off with 128,
yeah, okay,
there will be
log
64.
log 2 n,
Correct?
okay.
Log 2, and each of them is going to take 2 layers, correct?
Okay, fine, thanks.
Okay. So what we find is deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if recast using only 1 hidden layer, or even if you limit the total number of layers. If you give them a fixed number of layers, the ideal depth of the network depends on the number of input variables. It's log n. If you give it a fixed number of fixed depth, then the network is going to necessarily be exponentially wide if you want to capture the model function exactly. So an MLP is a universal Boolean function. but can represent a function only if it's sufficiently wide, sufficiently deep. And depth can be traded off for exponential growth of the width of the network. Now, the optimal width and depth depend on the number of variables and the complexity of the Boolean function, where the complexity is the minimum number of terms in the DNF formula for the Boolean function. Did all of this make sense? So give me a thumbs up, guys. I'd like to see it, 20 thumbs up before I move on. Thank you, right? So the story so far is that multi-layer perceptrons are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine. But a single layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower networks to express the same function. It could be exponentially smaller. So we've looked at Boolean functions, but then let's look at classifiers, right? Remember that MLPs in the end don't actually operate over Boolean variables. They operate over real inputs. And the MLP acts as a function that finds a complex decision boundary in the space of reals. We also saw in the last class that the perceptron with a threshold activation, which computes an affine term and then applies a threshold to it, basically computes a Heaviside step function. There's a linear boundary, and it's going to generate an output of 1 on one side of the boundary and a 0 on the other side. So this is the function it computes, right? We also call it a linear classifier because if you use 0 and 1 as class labels, the boundary between the two classes is linear. And we saw why Boolean perceptrons can be used for computing, why perceptrons can be used for computing Boolean functions. In this case, clearly, this perceptron is computing an OR, this perceptron is computing a NOT. And you can see why a perceptron cannot compute an XOR, because in an XOR, you need to go up and then go back down, whereas a perceptron can only either go up or down. It cannot it cannot compute something of this kind. That's why an XOR needs more than one layer of perceptrons, right? So here's a problem. Okay. 5 seconds, guys. All right. Let me stop the poll. And what is the answer? True, right? Perfect. So we got it. But then we found that once we know that the perceptron computes a linear boundary, you can compose more complex decision boundaries like this one. Can you please mute yourself? If you want a pentagonal boundary, you'd have one perceptron for the bottom boundary, one to the side, one for this one for this one, and one for this one, or all of their outputs. And only within the pentagon are all 5 perceptrons going to output a 1. So if the final neuron simply sums all of their outputs and compares it to a threshold of 5, this network is going to compute this pentagonal decision boundary. But then once you can compose a pentagon, you can compose more complex decision boundaries like this one. I can just attach 2 pentagons. I can have one subnet for the first pentagon, a second for the second pentagon, and then OR the lot, and I get this decision boundary. Or I can have other kinds of decision boundaries, ugly ones like these, and I do it very simply. I could decompose this decision boundary into many little polytopes. I can build one little subnet for each polytope and OR the lot. And if I did that, I'm going to get this decision boundary. So it can compose arbitrarily complex decision boundaries. But the thing to note over here is that the number of layers is actually, in these examples, it's 3, right? You could need more. So can I build these decision boundaries with only one hidden layer? Or let's take this simple example. Would it be possible for me to build an MLP with just one hidden layer, which composes this double pentagon decision boundary? Anybody? Do you think you could do this?
Yes.
How? Anyone? Okay, Logan, how would that be?
Well, we know that they're universal approximators, right? But if it's only one layer of neurons, then it's going to scale exponentially with the number of decision boundaries you need to make.
So you're giving me, yeah, they're giving me a high level answer. But so here's the thing. If you thought that you could just sort of somehow finagle these boundaries to get this kind of decision boundary, you'd find it's not possible, because these regions between the two pentagons are going to interfere. And so any threshold which captures these pentagons are going to also capture regions outside. Anything that excludes the regions outside are going to exclude some portions of the pentagons. So to see how you can do it, let's look at it. Go back and consider the simple polygon. Consider this simple polygon, the diamond. For this diamond, I'm going to need a network with 4 neurons in the hidden layer, right? And it's only within this diamond that all 4 are going to output the value 1. So if I look at the sum of the outputs of all 4 neurons, it's going to be 4 in the diamond, it's going to be 3 in the yellow regions, and it's going to be 2 elsewhere. So I can just compare the sum against 4, and I'm going to get the decision boundary that's this diamond. But this plot here shows you the actual sum. It's 4 here, it's 3 within these strips, and 2 elsewhere. This picture making sense to all of you? Yes or no? Okay. So if I want to have 5, a pentagon, same thing, 5 neurons. The sum is 5 only within the pentagon. It's 4 in these yellow regions and 3 over here and 2 here, right? What have you found? What do you observe about the yellow regions? They have reduced in size. Now, why am I worried about the yellow regions? Look at this yellow region. The sum here is 4, right? Now, if I try to compose a single hidden layer MLP for this guy, the yellow region where the sum was 4 for this pentagon, and the region where the sum was 4 for this pentagon would overlap, and you'd have parts of these white regions where the sum is actually greater than the sum within the pentagons, because the 4s for the 2 guys would overlap and give you an 8. And so you want these guys to be really small, right? These regions that are less than 5. The lowest you're going to get is 2. Does that make sense? Yes or no? Give me a thumbs up if that made sense, guys. I'd like to see 20 of those. Okay, so here it is for heptagon. The sum is 6 here, 5 in these regions, and eventually it goes down to 3. Here it is for a heptagon. What do we observe about the regions where the sum is not n, sum is not 7? So Mahati, yeah. You see the regions where the sum is 4? Yes or no? Okay. So if I try to do the double pentagon using just a single hidden layer, one set of neurons is going to give you this sum, correct? So each of these pentagons is going to give you some regions where those five neurons outputs sum to 4, right? But it's not in the pentagon. Yes or no? Nothing? So the 4 region for this guy and this 4 region for this guy will overlap, correct? Because the 4 region is going to be a triangle here, the 4 region for this guy is a triangle here. And so the sum becomes 8, which is greater than the sum inside the pentagon, right? You're trying to eliminate overlapping regions, exactly. And so what kind of shape will have no overlapping regions? Mahati, maybe you can answer me. Let me show you, right? As I keep increasing the number of sides, look at the sum. And what is the sum converging to? It converges to this beautiful cylinder where the sum is n inside the circle, and it tapers off very quickly to n over 2 outside the circle. In the limit, this is going to have, there's actually the formula for this shape that you would get. But in the limit, you can as being something like this, which is when n is very, very large, you're going to have a sum of exactly n inside this region, which will be circular, and a sum of exactly n over 2 everywhere outside. Does that make sense? Guys, yeah, right? And if I just add a bias of minus n over 2, now I'm going to have a sum of n over 2 inside the circle and 0 elsewhere. So if I just sum all of these outputs and use a threshold of n over 2 in the final net neuron, I'm going to get a decision boundary that's a perfect circle. But then I can take 2 of these subnets, which compose cylinders in 2 different locations, and still use a threshold of n over 2 over here. And what is the sum of all of these guys going to be? This guy, this subnet, is going to compose a cylinder here. This subnet is going to compose a cylinder here. The total network is actually going to compose 2 cylinders. And if I slice it at height n over 2, I get a decision boundary which is 2 disconnected circles. Does that make sense? Yes or no? Right, and so here's how you compose the double pentagon, right? It's not going to be exact, it's going to be an approximation, but you can make the approximation arbitrarily accurate by reducing the number of cylinders and packing them tight. And so here's what we get. A one hidden layer MLP can approximate any classification boundary with arbitrary accuracy. So a one hidden layer MLP is also a universal classifier, but then we find that the same thing could have been done with just 5, 10, 12 hidden neurons. Right? 12 hidden neurons. Whereas if I wanted to do this with one hidden layer, I'm going to need infinite hidden neurons, right? So this is what this means is that depth helps. But to get a better idea, let me look at a different pattern. Worst case decision boundaries, again for threshold activation networks. Look at this pattern. If I want this decision boundary, a naive one hidden layer neural network is going to need essentially hidden neurons and then infinite neurons in the hidden layer. I can do this with 2 hidden layers. Now this entire decision boundary is composed of 16 lines. So I can just get away with, so I need 16 neurons in the first layer to capture each of these 16 lines. And then there are 40 of these yellow highlighted regions in the picture. So I need 40 neurons in the second layer. And so this network with 56 hidden neurons in 2 layers can compute this decision boundary. But then, if I look at it carefully, so is this making sense, this figure does? Is the figure making sense? Yes or no? Please give me an answer. I hope Nimish, what did I lose?
The
Okay.
second layer I was not able to understand. Why
Okay,
do we have
so you understood
50?
the 16 lines, correct? You understood the 16 lines, correct?
Yep.
Okay.
Correct.
You understood it? Yeah, sure. Yeah, we can think of it as a fully connected network with zero weight for some of these things, right? Now look at this box. This box is composed of just these 3 lines, right?
Correct.
So I need 1 neuron for this box. I would need 1 neuron for each of the yellow boxes, correct?
Correct.
Right.
Correct.
So,
Right.
David, the 2 pentagon example would require the circuit. Okay. So here, there's 2 hidden, so you need 40 in the second layer. But then this is just an XOR over all the y's, the outputs of the, once I get these lines, if I call the variables output by the first 16 neurons as y1 through y16, the pattern is an XOR over the y's. I could have composed it using a standard XOR network. There are 16 y's, so there's going to be 15 times 3, or even 15 times 2 neurons for the XOR plus 46. So instead of 56 neurons, I would only need 57 neurons. I'd only need 46 neurons if I went beyond 2 layers, right? By restricting myself to 2 layers, with 1 layer it's infinite, for 2 layers it's 57. But if I go beyond 2 layers, it's only 46. Now, the difference is not great over here, but if I compose a grid of 64 lines, like so, then I'd need 64 basic linear detectors. There are 544 yellow boxes. So a 2-layer network would require 609 total neurons. But this again is an XOR over the 64 lines. So 64 lines is 63 times 2, it's 126. 126 plus 64. I'm going to need only 190 neurons as opposed to 609 neurons to compose this function. So even going beyond 2 layers, if I let it go arbitrarily deep, the network is going to be much shallow. Now this is a star. So Mengru, every time you cross a line, the output changes, right?
Cross which line?
So as you go along any kind of a checkerboard pattern is an XOR. So each of these lines is a feature. So you can now think of it as being axis aligned, because I've got the lines with these basic detectors. And then so if y1 fires but y2 doesn't fire, I'm going to get something. But if y2 also fires, the color is going to change, correct?
If y1 fires but y2 doesn't.
So meaning as you go from left to right, anytime you cross a line, the output changes, correct?
Yes.
So anytime the output of one of these guys changes, that's what crossing a line would be.
Right.
So it's an XOR.
So it's referring to the checkerboard part?
So the checkerboard is basically it's an XOR over the 64 lines.
But what about
Any
the region
checkerboard is an
outside
XOR.
what about the region outside of the checkerboard?
So once you come here, if you keep going here, there are no more lines, so the output will never change. That's all.
Okay, got it. Thank you.
Right. So the number of neurons required in a shallow network is potentially exponential in the dimensionality of the input. Alternately exponential in the statistical number of statistically independent features, but then there's a little more to it, which we will see. But the what we are adding to the story so far is that deeper networks may require far fewer neurons than shallower networks to express the same function. In principle, it could be exponentially smaller, so deeper networks are just more expressive, right? But that's for classifiers. What about arbitrary functions, real-valued functions? We've already seen that if I have a function of just one variable, a single variable x, I can compose a little network which computes this pulse. And then if you give me an arbitrary function of this kind, I can decompose this, the axis to many little regions, compute a little step, a square within the region, and then scale it up and compose the function to arbitrary precision. So we know that a one hidden layer MLP can model an arbitrary function of a single input. But then if you want it to be extremely precise, the number of neurons is going to be very large. But this is for a net function of a single variable. When you have functions of more than one variable, the generalization of this is a little more complex than you'd imagine. It turns out you have to think about it in terms of cylinders. So now we know that an MLP can compose a cylinder. If I have a very large number of neurons in that one in the single hidden layer. So one hidden layer MLP can compose a cylinder, right? If I just sum all of their outputs. And so if I want to compute an arbitrary function in high dimensional spaces, I'm going to have to partition the space and fill it with cylinders and scale them all to the appropriate height to approximate the function. So MLPs can actually compose arbitrary functions in any number of dimensions, even with only one hidden layer, as sums of scaled and shifted cylinders. This can be done to arbitrary precision by making the cylinders thinner. And so a one hidden layer MLP is a universal approximator. Does this make sense? Right. Okay, now here's my poll. Here it is. I'll give you only 15 seconds, 20 seconds for this, because I'm running out of time. Yeah, Vijaya. Answering is important. It just tells me that you're paying attention. That's right. It's okay. Let me stop this poll. What do you think the answer is, guys? False or true?
False.
False. Why? It cannot be exact, right? So you can approximate it to arbitrary accuracy, but the error is never going to be zero. And obviously, to answer Isaac, you're never going to use this method because you need infinite neurons, right? It can only be approximated. But if you let the network be deep, you can do this with a finite number of neurons for the same error. In fact, a very small number of neurons. So you get an idea that MLPs are universal functions, or more generally, universal approximators. They can approximate pretty much any function to arbitrary precision. But in all cases, it's important, if you try to restrict the depth of the network, you're going to end up requiring an exponentially large number of neurons to model the function. So deeper networks are better, right? That come across to you guys? Yes or no? Give me a thumbs up if you got it. I'll wait for 20 of those. Thank you. Appreciate it. So the previous discussion showed that a single hidden layer MLP is a universal function approximator It can approximate any function to arbitrary precision, but may require an infinite number of neurons in the layer. More generally, deeper networks will require far fewer neurons for the same approximation error. So this is true for Boolean functions, classifiers, and real-valued functions, but there are limitations. So there's something called sufficiency of architecture. Let's go back to this decision boundary, right? It is composed of 16 lines. So I need 16 neurons in the first layer and 40 neurons in the second layer. Now assume that I'm using threshold activation functions. If I have only 8 neurons in the first layer, would it be possible for me to still compose this boundary by simply increasing the number of neurons in the second layer or adding more layers, or whatever else? Why not? Anyone?
The first
The
layer
answer is
needs
no.
to capture all the features.
So here is what will happen. A network with only 8 neurons in the first layer may capture these 8 boundaries. So once you get past the first layer, the only information you will have is which region you are in, but finer distinctions are lost because, again, you're speaking of threshold activations, right? And so there's nothing you can do subsequently to recover this pattern. Make sense? In fact, even if the first 8 neurons capture these lines, you're still only going to be able to, once you get past the 8 neurons, you're only going to be able to decide which box you're in, but not where you are within the box. There's nothing you can do subsequently to recover the pattern. So how can you fix this? If I still want to use only 8 neurons in the first layer, how can I fix this? What is the real problem? Anyone? First, regardless of depth, every layer must be sufficiently wide. Every layer must be sufficiently wide in order to capture the function. Even if I gave you 16 neurons here, but gave fewer than 40 neurons in the second layer, you couldn't capture this function. And then you're adding more layers subsequently won't help. But then let's look at why this happens. This is because we use the threshold activation. The threshold activation gives you a 0 or a 1, right? So on one side of the boundary, it's 0, on the other side, it's 1. It doesn't tell you how far you are from the boundary, right? So once you get past this first 4 neurons here, all information is lost. You only know that maybe you're in the 0 region, but you do not know how far you are from the boundary. So if you want to know how far you are from the boundary, what do you have to do? You have to change your activation function. So instead of a threshold, you want something that goes smoothly like so, like a sigmoid. Now a sigmoid not only tells you when you have crossed the 0.5 line, but the value of the sigmoid tells you how far you are away you are from the boundary. And so if I used sigmoid activations over here, the graded nature of the activation will continue to give me information even after the input has been passed by the first layer. And I may still have sufficient information for me to recover the boundaries in subsequent layers. Does that make sense? Why do we need the distance to the boundary? So go away. Here, I need 16 lines, correct? If I have only the 4 lines here, if I only have 4 neurons, then you're only going to get this information. Can you recover the remaining 8 lines over here once you go past these 4 neurons? In this case, go away. Would you be able to do that? No. Well, I'm assuming if you can, I'm assuming that you get the point, right? So here you cannot actually recover the remaining lines. Whereas if I knew the distance from the boundary, then I can say, yeah, I've crossed this boundary, but then I'm here, and so maybe I can draw a boundary here. So having this information is key. Now, which means that that's telling you something more important, right? You want the activation function to be graded. Now, what's the good about the sigmoid function is that it's graded. But what's bad about the sigmoid function? Can someone tell me? What's bad about it? After you get past this point, the information about the distance from the boundary is lost, right? Once it gets to the close to the top, how far you are from the boundary gets lost. Instead, you want to have an activation function that continues to give you information about the distance from the boundary regardless of how far away you are from the boundary, which is why an activation function of this kind, which is the famous ReLU, is more useful than a sigma. So did that make sense? Right. So, okay, and what's wrong with this guy? Anyone? What's wrong with this guy? On the left-hand side, it tells you how far you are from the boundary only on the positive side. It doesn't tell you how far you are from the boundary on the negative side, right? So how would you fix it? Differentiability is not even something that's coming into the picture here, right? The fact that it's not telling you the distance from the boundary on the left-hand side is a problem, right? So you want to give it a different slope to the left-hand side so that you know there's a boundary, right? And you can find out the distance. There is a boundary, it must be nonlinear, but then you can also know how far away you are from the boundary on both sides of the boundary. So something of this kind, which continues to give you information on both sides, is going to be more useful than something like this, which is going to be more useful than something like this, which in turn is more useful than this stuff. Does that make sense? A leaky ReLU, that's correct. Right? And so narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded. But in order to compensate for not capturing the boundaries over here, you're going to have to make the network deeper and have more neurons downstream to capture the patterns, right? Mangrove over here for this leaky ReLU, right? Regardless of how far away you are to the right of the boundary, you keep getting information about the distance from the boundary. Same to the left. So the point is the perceptron has a very distinct boundary. This is something very different from the function you're trying to model, right? If I have the same slope for both, Siddharth, what happens? What do I get? I get a straight line, right? There's no nonlinearity left. So what happens if I have no nonlinearity left? Then it's no longer a classifier. It's not, and there's no distinction. Okay, all of my layers are going to collapse to a single layer. So the lessons so far are that MLPs are universal function approximators. They can model any Boolean function, classification function, or regression. Deeper MLPs can achieve the same precision with far fewer neurons, but must still have sufficient capacity. The activations must pass information through. The MLPs, there's a minimum width for every layer. And the minimum width for the layer depends on the kind of activation you're using. So for activations that pass information about the distance from the boundary on both sides of the boundary, then you can actually make the Yeah. So that y equals x is not a classifier, right? How are you going to decide when the output is class 1 or class 0? You can't, right? You need a nonlinearity. Anyways, so basically you can have, if you want to make the layers narrower, then you must have more expressive activation functions. And by making a layer narrower, you'd have to compensate for it. You'd have to make the network deeper and add more neurons downstream. So there's a final pole, which is, let me see if I have, I won't call it up, but I've already told you what the correct statements are. Is that first statement true? A network with an upper bound on layer width can nevertheless model any function by making it sufficiently deep. Is this true or false? False, right? Because we just saw that. Networks with graded activation functions are more able to compensate for insufficient width through depth than those with threshold or saturating activations. True or false? True, right? We can always compensate for limits in the width and depth of the network by using more graded activations. True or false? Beyond a limit, you cannot recover, right? So the third one is false. For a given accuracy of modeling a function, networks with more graded activations will generally be smaller than those with less graded activations. True or false? True, right? Because you're carrying the more graded activations convey more information downstream. So all of this leads to something called a concept called a capacity of a network. What kinds of models can it, what functions can it model? It's defined in terms of information or storage capacity, VC dimension, etc. There's a lot of work on it that we won't get into, but then you get an idea of what the capacity of a network is. It depends on how wide, how deep it is, and what activations you use. And a network with insufficient capacity cannot exactly model a function that requires a greater minimum number of convex hulls than the capacity of the network. I didn't call it up, friend. So there are lots of literature on the capacity of the network. We have something on the slides. Please look them up. I particularly like the one by Friedland and Krell because it's something everybody can understand. So the lessons today, MLPs are universal Boolean functions, the universal classifiers, the universal function approximators. A single layer MLP can approximate anything to arbitrary precision, but could be exponentially or even infinitely wide in its input size. Deeper MLPs can achieve the same precision with far fewer neurons. So deeper networks are more expressive. And more graded activation functions result in more expressive networks, right? So that's the end of this class. What we've seen so far is that MLPs can emulate any function, but how do we make them emulate a specific desired function? That's a different problem. What we've talked about today is their ability to model functions. What we will talk about next is how to make them model functions, training and MLP. So that's the end of the class. Thank you, everybody. I'll stay here for some questions if you have any. Otherwise, thanks for attending.